Hi, I'm Ms. Boom. Let's have a look at conditional probability. Here we have 10 shapes. If I ask you what's the probability of square, you simply say 3 out of the 10 shapes. But what if I ask you what is the probability if you try to pick it instead of me? Well, that doesn't matter, so we call that independent events. But if I ask you what is the probability of picking a square if you only had black ones to choose from, so only those 6 shapes, that is a condition that makes it different. So we say that is a dependent event. So independent means if I give you a condition that doesn't alter the probability, whereas dependent means I give you a condition that changes the probability. So today we're going to talk about conditional probability. The condition here being that we're given black. So in this case here, I gave you black. That's the condition. So we write it as the probability of square given black. So that line there is given black. So how would we do that? We look at, well, we don't have white anymore, so we can only use these 2 black ones. So that's the intersect of black and square over the only black ones. So this 6, which is a third. 2 out of 6 is a third. Let's have a look at this formula a little bit in more detail. So if A is square and B is black, then we can see in the Venn diagram that there's 3 squares and 6 blacks, and there's 10 in total, 2 of which are black and squares. 1 square is not black, so we get 1 there. And how many black shapes are not squares? We have 4. Sorry, that should be 6 minus 2 there, and that should be 4 there. And then which shape doesn't belong in any of them? That's the triangles. There's 2 on the outside, because 1 plus 2 plus 4 is 7, so A union B is 7, but there's 10 objects, so there must be 3 circles on the outside. So the probability of square given black is a third, as we saw before, so those 2 over the 6 black. So how would we write it as a formula? And before we continue, notice that the chances or the probability of picking black given a square is very different. So if I gave you only the square, so these 3 here, what is the probability of getting black? So ignore the rest. So if these 3 here, black, the probability of black, that means these 2 out of 3, so 2/3. So notice that when we write probability of square given black or probability of black given square, they're not the same thing. So probability of square given black means you are having all the black shapes and you're looking for square. Probability of black given square means you have all the square, but you want to pick black. So this is to summarize what I just said there. The probability of A given B is not the same as probability B given A. So what is probability A given B? So we can see that the probability of square given black, we had to look at the 2 black squares. We couldn't look at that one because we're given only black to choose from. So that is the intersection of black and square. So they're both black and square. So see, intersection. Over, and we looked at, we're only given black, so only black. So over black, not over everything. So the probability of A given B is the intersection over B. So remember, as given B, the second thing goes at the bottom. That's how I remember it. The second thing goes as the denominator. We can move this to this side to make it the multiplication rule. See, if we move the B to this side, so divided by B, moving to this side is multiplication. So A given B multiplied by B gives us the intersection. And likewise, if we talk about the other scenario, B given A times A, so remember the second thing in the bracket is your single probability as well, is also the intersection. We have to make sure that the probability is not 0. So this is called the multiplication rule. Remember the addition rule was A union B? Well, this is the multiplication rule, or A intersect B is the same as A given B times B, or B given A times A. So let's figure out the example 2. A group of 500 students were asked whether they prefer to wear hats or beanies. They also recorded whether they had long or short hair. So here we have a table. What is the probability of hats? Well, there's 375 people in total that wear hats out of the total of 500. Always simplify, that's 3/4. What's the probability of hats given long hair? So hats given long hair, so these are the only people we're allowed to choose from, long hair. So hats given long hair is hats intersect long hair, which is 225, over long hair, which is 300. Remember, A given B is the intersect, which is 225, over the second thing in the bracket, long hair. So long hair is 300. Simplify that, we get 3/4. Let's try another one. Probability of A is 0.6, B is 0.3, and B given A is 0.1. Find A intersect B. Well, we know from the multiplication rule that A intersect B is A given B times B, or B given A times A. So we have here B given A, so it's going to be B given A times A. So 0.1 times 0.6 is 0.06. How do we find our probability of A given B? That's the intersect over B. So the intersect we have here, 0.06, and B is 0.3, which gives us 0.2. You might want to do this again because I know it can get a bit confusing, the given sign, and why we multiply the B given A by A and not by B. We always multiply by the second letter. Example 4. The probability that Jacob wakes up early is 0.15. The probability that he eats breakfast is 0.08, so tiny. And the probability that he wakes up early and eats breakfast is 0.03. Given that he wakes up early, what is the probability that he eats breakfast? So let's read that again. Given that he wakes up early, what is the probability he eats breakfast? So what goes first in the in the bracket? So the thing that's given is always the second thing in the bracket. So breakfast, given, wakes up early. So that's how you should interpret the question. Always put the given after. So we know that it's given to us that wakes up early is 0.15, eats breakfast, let's call it B, 0.08, and breakfast and wakes up early is 0.03. So and, remember it's intersect. Now, how do we figure out what's the probability that he eats breakfast given wakes up early? See, even though the sentence says given wakes up early, then it says what is the probability of breakfast. I always try to read it as given as the second thing because I'm going to write it as the second thing. So breakfast given wakes up early is the intersect over the second thing, which is wakes up early. So you have to write in the right order, otherwise you'll put the wrong thing at the bottom. Second thing at the bottom. So intersect is 0.03. The W is 0.15. So we have 0.2. So here we have the Kano map, and let's have a look at the formulas. So the multiplication rule, so when we rearrange it, A given B times B is the intersect, or A given B dash times B dash is the intersect. What can we do with that? Well, we see from the Kano map that probability of A is adding these two, so A intersect B and A intersect B dash. So if we join these and these, so substitute this A intersect B over here and this over there, then we can see that the probability of A is simply A given B times B plus A given B dash times B dash. So this is the law of total probability. Example 5. Luke has 3 bags of lollies. In bag 1, there are 3 mints and 3 toffees. Excuse the typo. In bag 2, there are 3 mints and 2 toffees. In bag 3, there are 2 mints and 1 toffee. So different amount in each bag. Luke selects a bag at random and then selects a lolly at random. Find the probability that he chooses a mint from bag 1, or a mint in general, or bag 1 given that he selects a mint. How do we solve this? Well, let's do a tree diagram where the first event is what bag he picks and the second event is what lolly he picks, whether it's a toffee or a mint. So the chances of getting any of these bags is the same, it's a third, but the chances of getting the mint or toffee depends on the bag. Let's go read the story again. In bag 1, there are 3 mints and 3 toffees. So the probability of picking toffee and mint is the same, a half each, or 3/6. But in bag 2, there are 3 mints and 2 toffees. So 5 altogether and only 2 toffees. So 2 out of 5 for toffee and 3 out of 5 for mint. In bag 3, there are 2 mints and 1 toffee. So 3 altogether and only 1 toffee. So 1 out of 3 for toffee and then 2 out of 3 for mint. So we can see that it's conditional probability because whatever the lolly, the probability of the lolly depends on the bag. So dependent. What is the probability of picking a mint from bag 1? So a mint from bag 1. So bag 1 and it has to be a mint. So that is a half times a third, or a third because we picked the bag first, times a half, which is a 6. What's the probability of picking a mint? Well, he can do mint from bag 1, mint from bag 2, or mint from bag 3. So bag 1 would be a third times a half, bag 2 would be an all mints plus, bag 2 would be a third times 3/5, and then we have or, so plus again. Bag 3 is a third times 2/3. And bracket it all up, and then it's a 6 plus 3/15, or 1/5, plus 2/9, which adds up to be 53/90. Now, what is the probability of picking bag 1 given that he selects a mint? So now we have to do the intersect of those two over mint. So the intersect of those two is bag 1 and mint. Bag 1 and mint is a half times a third, which is a 6. And mint, we've worked it out there. Choosing a mint was that monster. Remember, we had to choose bag 1 and mint, or bag 2 and mint, and bag 3 and mint. Be very careful with that. So probability of mint is very scary, 53/90. Try doing that part again. So simplifying that fraction is 15/53. Okay, you might want to do this one again. Be very careful about the mint part. And we can see this is dependent probability because depending on the bag you choose, the probability of the second event changes. Thank you for watching and I'll see you next time. Bye!